to class? You do? Okay, good. I'm sure it's there. So, a guy went to the doctor, and he said, "Doctor, I've broken my arm in several places." And what do you think the doctor said in response? That would be a cruel doctor.
That's humorous.
Nice.
Is that right?
No, but that's not what I'm looking for. But that is a good answer. Doctor, I've broken my arm in several places. What advice did the doctor give him? He said, well, yours was good. I like that answer. So he went in and he said, "Doctor, my arm's broken several places. What do I do?" And the doctor says, "Stop going to those places." I gotta have a laugh track because I was recording that one. So I'm gonna have to press a button so that. Okay.
No, we laughed. It was just like,
You did. Well, you laughed. Everybody else joined in after a good 5 seconds. Okay. So, in this question, we've got a quarter in a fish tank, and I'm asking you, I should show the people at home. Here's the question. It's a bit long. The main idea is that there's a quarter in a fish tank, and you really want to go to the arcade so you can use it. So you reach, and your eye sees the quarter in a certain spot, and the real question is, knowing how light rays bend, where do you actually have to reach in order to actually get that quarter? Do you have to reach in front of, behind, or right on with where the quarter appears to be? So I'll just draw you what those possibilities look like, and then we'll see what you think. So if this is the fish tank right here, water, and we'll say that the quarter is, well, let's say here's your eyeball, and you see the quarter, and the quarter appears to be right here. So when you're looking at that quarter, that's where it seems like it is. Do you have to reach behind where it appears to be, right on with where it appears to be, or in front of where that quarter seems to be in order to actually grab it? Any thoughts? In front of it, perhaps?
Well, what's in front of it? What's in front of it for that?
Oh, just in front of it would be this side.
Behind it.
Behind it, Olivia?
I would say in front of it because it's in water, right? So
Right.
if it bends, so it could be like here it was more in front of it, like farther than it already
Sure.
is. So you go in front of it.
So if you're thinking about the actual object, let's say that we put the actual quarter in here. I think I see where you're going with this. Let's say the actual quarter is located right here. You're saying it has to do with how light's going to bend. So let's say the light comes up, the water. What direction is that light going to bend after it leaves the water? It's going to bend across. Yeah, exactly. In order to get to your eyeball. So where does that image appear to be in your brain? Further behind. So your brain thinks that the quarter is over there. So you have to reach what? In front of or behind?
Oh no, I don't know if that's in front or behind. I don't know.
Yeah,
No, you would have to reach behind because it's behind than what you
If
actually
it's right
think
here,
it is.
you gotta
so
grab
you
it.
go.
Where it's at, so in front of it, I think.
But then if you
This
go
is-
in front of it,
That's
way
the real
farther.
one, so that's behind.
Yeah, so in front, right? You gotta reach in front.
you do have to reach in front. Yep.
Oh,
Yeah,
right.
tell me no. I know I'm right.
Because when you see the image, it appears to be right there, but the real thing is in front
Yeah,
of
so
that
if
image.
It's right there. That's in front of the actual object. So when you have to reach behind.
Well, this is behind the object. You're looking at it
No,
from here.
because if you're looking at it like that, that's in front and that's behind.
Oh, we're just confused on on those words, yeah. So for me, anyway, if if something is right here, I would think in front of it would be right here.
Why would that be?
And
in front
behind
when
would be
there's something in
back
front
there.
Of it?
That's behind too. I feel like I don't know.
No, because
That's why
if I'm looking like this at it, this is in front of. Wait.
Exactly.
Oh.
So, yeah, the main thing, you got to reach closer to where your body is if you wanna avoid that issue.
You should have said closer.
But for the final exam, it's going to be listed as in front of. That's the one you want to pick for that.
That's gonna confuse me.
So, in terms of this worksheet, today was a day where I was going to have you guys like work in groups on it, try and help each other out through it. I feel like maybe it would just be better if we kind of went through it together. What do you think about that? Okay. So let's go through worksheet number 5, bit by bit, problem by problem. There will be no homework by the end of the day today, and we'll all be happy. Yes? Yes, you may. Let me get you passed. Just fill that up the rest of the way for me. September 9th and 10:30.
Okay, so.
So when we're taking a look at the worksheet, let's look at number 1 and 2 first. These should go by pretty quick. This is 209. So number 1 and 2, we've got a bunch of light rays. Listen up, guys. Here we go. Number 1 and 2, we've got a bunch of light rays. They are at first going into the water. In the second problem, they're going out. So for all the light rays that are going in, for problem number 1, I can probably just draw one of these for you. It hits the water. I'm going to put my little normal line in because it's a habit that is a good thing to get into. When that light ray goes into the water, is it bending down or is it bending across? It's going to bend down, exactly. And the reason for that is because the air is a fast medium. So the light ray is traveling quickly in that fast medium, but then eventually it reaches the water. In this example, the car's wheel reaches the water first. For a light ray, it would just be this side of the light beam. And so, if you think about it, this wheel is now moving slower, this wheel is moving faster. That's going to cause the car to turn downwards. And that's why and how light rays behave in that fashion. If you want to get specific about it, the bigger the angle this is, the bigger the difference is going to be when it goes into water. But the main thing you have to know is that these light rays are going to bend down. Did you have a question?
No.
Okay.
But slanted-ish, right?
Yeah, slanted.
Not just.
Right, it's not going to go straight down.
Yeah.
Oh, I do have a question.
Yes.
But it's like.
The straight one.
Oh, the straight one will continue straight through.
Oh,
Yeah, there won't be any change in angle if it's coming straight down.
it won't. Doesn't it like it doesn't shift to the side at all?
No, I mean it'll start exactly at that spot, and then it'll just curve down a little bit. What do you mean by shift?
Like. I can't explain.
Oh, the one going straight down?
It just
No.
goes to the side at all?
No, one going straight down would just continue right on down.
Oh,
And that'd be the same feeling if there was, right?
Good. So number 2, you can probably guess. You know, the cool thing about this is I just need to change the direction of the arrows. So for number 2, when light's coming out of the water, of course on the worksheet it's going to the right, but whatever. As the light's going out of the water, it's going to bend across. It's not going to bend towards the vertical like it did in number 1. Same thing with this one. If it's going straight up, it will continue straight up. And the reason for that is the same. If you think of a car going from a slow medium to a fast one, it's going slow, 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 slow. Now the top right wheel is moving faster than the front left wheel. And that means the car is going to turn across like this. The light ray is going to do the same thing. Was it?
The exact spot in my brain.
Good. I'll give you a stamp quick. We just finished 1 and 2.
Oh.
Yeah. Further questions on 1 or 2? Okay. Page number 2 is probably going to take most of our time here. Number 3 and number 4. These should be interesting. So for number 3, I really just got to do the top part, because both 3 and 4, you can see the middle part, you're just going straight through. And whatever the bottom part is for number 3 and number 4, the light ray is going to do the same thing, just in the opposite direction. So as long as we can figure out the very top of number 3 and 4, we should be okay with this. So think about light. It's traveling in a fast medium right now, and then it encounters a glass block. So when this light ray goes into the glass block, will it bend down or will it bend up? Think about the car analogy.
Up. Down.
Well, you're half right.
Right through.
Maybe just straight through?
Horizontal. Yep.
Because this is a smaller example, I'm going to give
Because if it's
smaller
glass,
car.
like, can't go through.
Well, it will go through, but that light ray is going to change direction because glass is a lot slower than
Then
air.
Down.
Down, perhaps.
Yeah.
How many people think the light ray is going to go down? How many think it's going to go up? How many think it's going to make a funny shape?
Oh, maybe it's that bad.
All right.
Gosh, it's a smaller car.
Okay. I can have so much fun with this camera. I'm only now beginning to see the possibilities.
I'm gonna have to watch that.
All right. So here comes the car. Oh, I gotta turn the elevator on. There we go. So here comes the car. It's going in straight, and this is the fast medium.
Wait, sorry.
Yes,
You know when you said the elevator thing?
Yeah.
You hear the elevator?
I do. So we're going in the fast medium. It's a weird day, isn't it?
Yeah.
And now we begin to enter the slow medium. Yeah, it's going to go down because the front right tire is now going to move slow. The front left tire will move fast, causing the car to turn down. Furthermore, when we reach the other end, now the front left tire is out of the slow medium and into the fast one. So this tire is now going to be moving faster, causing it to turn down even more. So the light ray is going to change directions twice. At first it's going to go down a little bit, and then when it exits it's going to go down even more. And I would put another normal line in here. So that's the sort of thing you would have for the top of number 3. And the bottom would be the exact opposite. It would go up. Sure. So the light ray he's coming in here. So here comes the car. Which wheel enters the glass first, top or bottom? The top one. So that means this wheel is slowing down. So now the bottom wheel is going faster. That causes it to turn upwards. And then when it exits, you can see the front right tire, or the bottom tire, I guess, is exiting first. So now this one's going to be moving faster. And that causes the car to turn upwards. All right, we'll take a look at number 4 then as well. This will be the top part of number 4. Yep, middle's going to go straight on through. So for number 4, here comes the light ray, and it enters the slow medium, and it appears that the top tire is going to get in there first. So that one's going to be slow. The bottom wheel's going to be going faster. It's going to cause it to turn upwards. And then now the bottom wheel exits first. So now this wheel is in the fast medium. It's outside the glass. It's going to cause it to turn upwards even more. So as you would probably guess, it's the opposite of number 3. Opposite would be true of the bottom. Questions on 3 or 4? And this is going to kind of provide us with a good foundation for what we're going to begin tomorrow, which is lenses. And those are going to be fun. Yeah, that's a kind of lens. In the same way that we have converging and diverging mirrors, we have converging and diverging lenses.
For glasses, is that what makes it nearsighted? Like, makes you see farther or closer?
Yep. If you are farsighted, and you can see things far away but not close up, then you've got converging lenses that bring light rays together. If you're nearsighted, like me and most people, your glasses take those light rays and they spread them out. It's like if I put my glasses, oh, you can't really see, but I bet I could help you to see this though. If I shine a light through my glasses, you can see the light rays around the lenses, and that's because it's taking the light rays and spreading them out. And that's something we'll talk about more tomorrow.
What about if you're just like blind? Like it's just blurry all around.
You're probably still one or the other, nearsighted or farsighted. I'm not sure if there's people who are both at the same time. Probably there must be something. Yeah, I'm sure your eyes can get really messed up.
Yeah.
And there's more issues than just the lens in your eye not focusing at the exact right location. All right, so let's take a look at the next 4 problems, which will probably take up most of the time here. So these are Snell's law. We want to make sure that we're okay with some of these. Number 5, we've got a light ray coming in at 40 degrees. We do not know the exit angle, but we do know that water is up top. Water has an index of refraction of 1.33. Glass is on the bottom. That has an index of refraction of 1.5. And that's listed for us. So we got to figure out what angle this light ray is going to make when it goes into the glass here. And in order to do this, we need Snell's law. So, Snell's law is on your formula sheet, it's in your notes, and it looks like this. N1 sine theta 1 equals N2 sine theta 2 And we just have to plug in the numbers for those values. So n1 sine theta 1, these are going to be your values where you begin. We begin in water. So we'll start by inserting these numbers in for those values in the equation. So the index of refraction of water is 1.33. The sine of 40 degrees is going to come next. And again, this is all happening in our first medium. In the second medium, we've got glass. So that's going to be 1.5 times the sine of the angle that we're looking for. I'll say theta g for the angle in the glass there. Any questions on why the numbers are where they are here? I'll make this a little bit more like a 5 and less like an S. There we go. So in order to solve this kind of a problem, then, we've got two steps we got to do. Number one, we got to get rid of the 1.5 over here. So to get rid of that, we got to divide both sides by it. So 1.33 times the sine of 40 degrees, all divided by 1.5. And that'll be equal to the sine of the angle. So again, from here to here, we're just dividing both sides by 1.5. That's why it lands right there. So then the final step is to get rid of the sine. What do we got to do with this? What's that? Inverse sine, absolutely. All you do to go from here to getting this angle by itself is you just take the inverse sine of the left, and that'll make that sine disappear because of math. Because it ends up being useful in a lot of ways, even if it can be annoying at times. And that'll give us our answer. Now, well, first off, any questions on where any of this came from? The cool thing about this is, once you have this set up, it's the exact same way to solve each and every one of these problems. You can.
The negative one for the sin on the left side.
That's just inverse sine. When you're getting this sine from this side to the other side, you're essentially, instead of dividing both sides by sine, you got to take the inverse sine of both sides. If you take the inverse sine of sine, that goes away, and then you're left with the inverse sine on this side. So that's just a button on your calculator. Now, when you're typing this in, you don't want to type inverse sine 1.33 times sine of 40 divided by 1.5. You want to have, if you're doing this with a graphing calculator, as I think most people are, you probably want to have this whole top thing in its own parentheses. Because you don't want your calculator to think that you're doing sine of 40 divided by 1.5. That would not get you the right answer. Yeah.
But you can do a fraction on the calculator.
Yeah, you can do that if you want. What does it look like if you do a fraction, you mean?
It looks exactly like that. Yeah.
Like this?
Yeah, so you press what is it? Alpha y equals, and it gives you a fraction method, and you can just plug it in
Okay.
on the top and bottom.
I'm not familiar with that, so if you're cool with that, you go right ahead. Yeah, that sounds good. The way I do it, again, I don't use a graphing calculator. I would type in this number into my calculator, and it would give me a number. And then I would divide that number by 1.5, and then I would just take the inverse sine of whatever that is. That's just the easiest way for my brain. Anyway, if you go ahead and do this, you'll get 34.7 degrees. If you're having trouble with this, and you need help inputting these numbers to get the right answer, see me at some point. Questions on number 5? Okay. Let's look at number 6. I think we'll skip number 7 because number 7 is like the exact same as number 5. Just different numbers. So let's see if we can get through 6 and 8, and then we'll tackle the back side of the worksheet. Number 6 looks tricky, but it's just how it looks.
I do not think I know.
Did anybody for this one end up with 52.9 degrees?
I got 1.8.
That's okay. This one, it looks so crazy, and it looks so tricky, but it's really not too bad, and I hope you see that as we go through this one. So we've got ourselves a fancy little triangle. It is a right triangle. The light ray is coming in straight away. So we've got water. So we've got water on the outside. It's got index of refraction of 1.33. On the inside, we've got glass. Glass is 1.5 again. Now, when this light ray goes from water into glass, what's it going to do when it goes into the glass?
It's gonna go straight through, but then it's gonna go back out.
Exactly, yeah. So when it first goes into the glass, it's going to go straight through. It's not until you get to this angle here that we're going to change direction. As Brooke said correctly, when it gets to this position, it's going to refract. And so in order to figure out what direction it's going to refract, we got to think it through. So here comes our light ray. It's moving fast now. It's moving slow, but it's still going in the same direction. Now the front right tire, or the bottom tire, is out of the slow medium. Now this one is in the fast medium. Yeah, so this is going to curl up a little bit now.
Oh, wait. What? Wait, why wouldn't it go down?
So
Because if the fast one is
So now we're in the slow medium, right? So now we're going slow, 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 slow. Now this tire is in the fast medium, so it's going faster. And so if this tire is going faster than the other one, it's going to cause the car to turn this way. So we're going to be angling up just a little bit. And because this is a 45, 45, 90 triangle, that means you know what this angle is. What is this angle? Yep, 45 degrees. So if we know that angle's 45 degrees, we got to figure out what this one is. Angle G, I'll call it, for angle, I should call it W. The angle that it's making when it goes into the water. So this is another equation just like the one that we just did. So for Snell's law, N1 sine theta 1 equals N2 sine theta 2. In this case, before we change direction, we're in glass. So our N1 is going to be 1.5. Our angle is 45 degrees. And that's equal to the index of refraction of water, which is 1.33, times the sine of the angle it makes when it goes into the water. And we got to solve for that angle. Just like last time, step 1 is to divide both sides by 1.33. And so that brings us to the sine of the angle. And in order to get rid of the sine, we got to take the inverse sine of both sides. And when you calculate that out, does anybody get anything?
I got 52.9.
52.9 is right on the money. Questions on this one? Cool. All right, so let's take a look at number 8, and then we'll do the back side. The thing with number 8, I'll leave this up here. The thing with number 8 is it's a word problem, and word problems suck. So what you want to do is you want to draw it out. So it says we've got light going from air into a plastic block. Maybe something like this. Incident angle is 25 degrees. Refracted angle is 21 degrees. And this up here is air, so the index of refraction of the first medium is just 1. So now we have to use Snell's law to figure out the index of refraction of, I'll just say N2, because we don't know exactly what the index of refraction is. It's plastic, but we're not exactly sure what the number is. So in order to solve for that index of refraction, we got to use Snell's law and plug those numbers in. N1 is going to be the index of refraction of air, which is 1, times the sine of the angle it makes in the air, which is 25 degrees. That's equal to index of refraction 2 times the sine of 21 degrees, because that's the angle it makes when it goes into the plastic. And to finish this off, all you got to do is divide both sides by the sine of 21. The problems where you are solving for indices of refraction are usually easier than the ones when you're solving for angles, because you don't have to mess with the inverse sine. So when you plug your numbers into this, you should end up with 1.18. And indexes of refraction are unitless. So it's just 1.18. Further questions on this side? Cool. So if you're going through these problems, you do want to make sure that you can put these into your calculator properly. So make sure that you do that. And if you have issues with the parentheses or something, come and see me and I can help iron that out for you. Let's take a look at the back side. Use the light rays to find out where the underwater image appears to be. This is kind of similar to the question we had at the beginning of class. We got our 2 eyeballs, and one sees a light ray coming like this. The other one sees a light ray coming kind of like this. So the question is, where does the image appear to be? Remember how we always said that light rays going into your eyeballs, your brain automatically thinks they've been traveling in a straight line forever? So you would use a straight edge and just follow these light rays back. Wherever those light rays cross is where your brain would think the image was located. So if you do it properly on the worksheet, it's a ways above where the actual object is located. All right. Letter B. If one of the light rays is in the tank and it hits the surface at a 35-degree angle, what angle will it enter the air? So with this one, you're doing Snell's law like we did in the other examples. I won't do the entire thing, but I'll get it set up for you. So the light ray is coming out at a certain angle, hits the surface at 35 degrees. So 35 degrees goes right here. Index of refraction of water is 1.33. Index of refraction of air is 1. So you'd use Snell's law to figure out what angle this is, the angle it makes in the air. And that would be just like the two other examples we did from page number 2. The answer you should get is 49.7. So if you got that, you're in good shape. Letter C, now suppose the incident angle is 80 degrees. So instead of using 35 degrees in your calculation, you would use 80. And guess what your calculator would say? Error! I can't handle this. And that would be just fine, because when your calculator spits out an error, that means you have total internal reflection going on, where the light is not going to exit the water. It is going to hit the top, and it is going to bounce back, never to leave. Letter D then says find the critical angle for the water-air interface. So we can do that pretty quickly. Critical angle is equal to the inverse sine of N2 over N1. So again, N2 represents the index of refraction of the material you end in. This is the index of refraction that you begin in. N1 is where you start, N2 is where you end. So for water, it would be the inverse sine of 1, because that's the index of refraction of air, where the light's trying to get to. But it begins in the water, so it's 1.33 in the denominator. And when you do that on your calculator, you should get 48.8 degrees. And what that means then is if you make that angle 48.8 degrees or bigger, that light ray is not going to leave this tank of water. And of course 80 degrees is much higher, so it's not going to leave. That's why you got your error. You can hang on to this worksheet. I'll collect it tomorrow. See you then. Here, I'll stop this quick.